Okay, last but not least, this is segment 3 on the first outline. If you turn to page 510, a very famous neuroscientist by the name of Donald Hebb, way back in the 40s and early 50s, thought that if we're going to learn things in terms of learning and memory, that there must be something going on in the cell assembly in terms of the neural circuit that must change. And he proposed this idea that there must be a circuit that somehow changes in the brain when we remember things like this. So I think he called it the reverberating circuit, that he thought that if you learn and remember something, there must be some sort of activity that changes in the brain for this. And what we're going to find out in this last little bit here, it looks like on page, 513, you can actually see a little Skinner box here. But what we're going to cover in this last unit is the idea of finding out what Hebb was talking about, and a very interesting phenomenon that seems to take place in the hippocampus in the brain. Now, if you remember, we've talked about the hippocampus before. Now we're on page 524, and it's been alleged that the hippocampus is a very important structure in the formation of memories in the mind. And so research has really focused on the idea of, once again, cognitive neuroscience. Can we see some changes in memory that somehow map to changes going on in the neurobiology of the hippocampus? And there's been a very interesting phenomenon shown, and I'm going to share this phenomenon with you. It's a phenomenon known as long-term potentiation. And if you look on 524 and 525, I'm going to explain the procedure that they use. If you look at figure 14.21, you can see they show different areas of the brain, including in the limbic system, the hippocampus. And if you look at the bottom picture on 1421, it turns out that there are 3 synapses in the hippocampus. CA1, can you kind of see that in there? CA1, CA3, and there's another pathway as well in the dentate gyrus. Those are 3 synapses in the area. Now, just for the sake of argument, just to show you that neuroscientists have a sense of humor, you might be saying to yourself, well, what does CA stand for? CA stands for corno-ammonis, which, the book says this correctly, which actually refers to the idea of a seahorse. When neuroscientists looked at the picture of the hippocampus, they thought it looked like a seahorse. You don't have to write that down. Because God knows there's enough other stuff to write down here. So what scientists have actually done in a very interesting study is they've basically gone in, and if you go into the hippocampus and into one of these synapses, what you can actually do is you can put in a little electricity in the presynaptic area, and then after you put in a little electricity presynaptically, you can measure postsynaptically the EPSP. You remember the EPSP? No, it's not the sports radio station. The EPSP, ESPN. EPSP stands for excitatory postsynaptic potential. And what you do in the first phase of this long-term potentiation study is you put a little stimulus into the presynaptic pathway, maybe in CA1, and then you measure out in the postsynaptic area the EPSP, and you'll find if you put a little electricity in, you'll measure a little electricity out. No big deal, right? So that's phase 1. Now in phase 2, they do something a little different in this pathway. They actually dissect these pathways out of the brain, and they do this in little petri dishes. What they do in phase 2 is they take into this presynaptic pathway, they deliver what's called a tetanus. It's a brief, intense series of electrical impulses. They put tetanic stimulation in, and hopefully somewhere in your book they say that. If it looks like 524, bottom of the first paragraph, they basically put a lot of electricity in. So of course, if you put a lot of electricity into the presynaptic pathway, and then you measure out at the postsynaptic pathway, what do you think you will find? Well, hopefully you'll say they found that there was an increased amount of EPSP postsynaptically, a lot of electricity. And that's exactly what they found. You put a lot of electricity in, of course you'll find a lot of electricity out. But the real interesting part of this study comes from what is shown in figure 1420. And in figure 1420, what they basically do is up to a day or two later, even up to 96 hours later, 3 days later, they'll put one single pulse back into this pathway. And what's really unique is when you put one simple pulse back into this pathway, all of a sudden, if you deliver one pulse, you'd normally expect just to get a little electricity out, but they actually find one pulse in leads to a whole huge response electrically out, as if this area has become what we call potentiated, increased. So the phenomenon of long-term potentiation is actually an electrophysiological phenomenon. What they do in phase 1, a little stimulus in presynaptically, you measure out. Postsynaptically, you have a little electricity out. Phase 2, you put a really strong stimulus in, tetanic stimulation, T-E-T-A-N-T-I-C, tetanic stimulation in, and you find that there's a strong EPSP at the postsynaptic side. But then the really unique part is phase 3, where you put a little tetanic stimulation in. And if you put a little tetanic stimulation in, just one pulse, you see a huge response out. And they call this long-term potentiation. So that is the idea of long-term potentiation. As far as tracing this some more, I'm going to try not to go into too much detail for you. They've actually really figured out exactly what's going on in the brain, and it seems one of the most important neurotransmitters that allows this long-term potentiation to happen is glutamate. It seems that this strong stimulation, if you will, during phase 2 basically removes some obstacles from the brain and basically allows glutamate to bind really well postsynaptically. That's between the presynaptic stimulus and the postsynaptic measurement. And so they basically find that glutamate basically starts working a lot longer to allow this change to occur. And the reason people are really excited about long-term potentiation, here's kind of the end of the story, if you will, and we've had enough stories anyway, is what they believe to be so exciting about this is they think that this might be what occurs when you remember something. So let's say you're studying for a test, if you will. This is just a cognitive analogy. You cram, you study really, really hard. You might call that in a way mentally tetanic stimulation. And then you come to the test and somebody says, what is memory? And just one question for you leads you to remember all of these things. Well, maybe that's the one stimulus that's leading to all that electrophysiological reaction. So this is called long-term potentiation, and we find that in the brain it happens in the hippocampus. It might be the neurobiological root for memory, and it seems as if glutamate is really involved in this process in some way. Page 525 goes into more detail here, but I don't know, I think I've given you enough information here. And they believe these are the roots of how memories form in our mind. So hopefully all of this makes sense. I've been babbling on for a long time, but I hope this makes sense too. Thanks. Bye-bye.